Hello everyone, this is Aditya and today we'll study sequence series in one shot. So let's directly come to the topic and please do like, share, subscribe my channel and now let's start the video. Okay, so we will basically study the convergence test, right? You all know what is sequence, what is series. Sequence is a set of numbers which are written according to some pattern and are separated by a comma, right? And series is just the summation of those terms, right? Okay, this is the basic idea, right? So we won't discuss much upon it, right? So now let's start with the first test. Test 1. We are studying the convergence test, that whether a particular series or sequence it is ending, it has a terminating value or not, right? Okay, so let's see. Test 1. We will study integral test. We won't go into the proof because we don't have much time, right? So that is why we will study in a very concise way, right? Okay. Suppose you are given summation f of x I, right? You are given this and I goes from 1 to infinity, right? So what does this test says is it says that if you integrate it from 1 to infinity of fx dx, right, from where the limit starts. For example, if it would have started from 2, then you would have started from 2, right? Okay, so if it converge, then you say that this series converge, right? It implies series converges, right? Okay, and if it diverge, we say that the series it diverge, right? Okay, I hope you are understanding it. Okay, so let's see. This was the first test. We will see the working in couple of minutes, right? But first we will study the all the test in a one go, then we will start with the problems. Okay, so test 2, you all can note this all this. Okay, it will better. It is also known as comparison test, right? I am not writing the complete thing because it will take more time. So suppose if you are given two series un and vn, right? Okay, right? Okay, so if un is less than vn, right? Okay, the summation of this is less than this. Okay, this implies if un converges, if vn converges, sorry, then this implies that un should also converge. Why? Because this summation is less than this, sorry, un is less than this, right? So if the bigger term is converging, then it is important for the un also to converge, right? Okay, and if un is diverging, then it implies that vn will also diverge, right? Okay, I be understanding. If the smaller thing is diverging, then obviously the bigger thing will also diverge, right? Basic idea. I'm not using the exact terminologies because it will be confusing also, so I'm trying to be very crisp and clear, right? Okay. So you can merge all this and you can say that limit as n tends towards infinity of un upon vn is equal to some lambda. Suppose it is equal to some lambda, right? Okay, and suppose if it is finite, right, then there are two conditions. Suppose you calculate vn, and if vn is diverging, right, then this will imply that un is also diverging, right? In this case, when lambda comes out to be a finite value, right? Right, and if vn is converging, then it implies un will also converge, means they both will go together, right? Whatever, for example, if one is diverging, then the other will also be diverging. If one is converging, then the other will also be converging, right? I we are understanding it. Okay, I we understand, right? Okay, so in this case, the limit as n tends towards infinity, un upon vn, right, is equal to lambda. I hope you understood it, right? We will see the problems soon. Okay, now there's one more thing which I need to tell. um, Suppose theorem or something like this. summation from I is equal to 1 to infinity 1 upon I raised to the power p is convergent when it is convergent if and only if p is greater than 1, right? For this value it is only converging. Okay, you should understand this, because obviously if it is a negative value it will become all the terms will come in the numerator and it will make the summation a very big term, right? But if it is in the denominator then it will be fine. Okay. Okay, so now let's come to the third test. Okay, we will see the problem soon, don't worry. Okay, just try to bear with this right now, just try to understand a bit, right? Okay, because we don't have time literally. Okay, so we will try to finish everything as fast as we can, and obviously you should understand it also. I will try to do like that only. Okay, now the test 3, it is a very simple test. Test 3, let's see what is it. D'Alembert's test. Okay, D'Alembert's test. Okay, I hope the spelling is fine. Yeah, D'Alembert's ratio test. And what we do in this is, for example, if you have a series, right, you calculate the unth term and you calculate the un plus 1th term, right? Okay, you calculated. Now you do limit as n tends towards infinity of un plus 1 by un, and suppose it comes out to be some value lambda, right? So if lambda is greater than 1 then the series is divergent, right? Okay, if lambda is less than 1 then the series is convergent, right? And if it is 1, if lambda equal to 1, you can't say anything, right? You need to apply the other test then. Okay, and one more thing to be noted is that if limit as n tends towards infinity of un is not equal to 0 but some other value, then in that case we say that the series is automatically divergent, because the last term is not become 0, right? That is why it will go on till infinity and the sum will become an infinite term, right? Okay, so basically now we are coming to the fourth test, test number 4. I you are understanding it, right? Okay, it is like bit logical. If the consecutive terms are greater than each other, then it will imply that the series is divergent, right? This is the next term, this is the previous term, you are taking the ratio, and if it's coming greater than 1 it will be obvious that it is divergent, right? Okay, so test 4 is Cauchy root test, right? Yeah, Cauchy root test. Okay, so basically what we do in this is you assume, for example, there's a series summation of ui, right? Suppose, and obviously u1 greater than u2 greater than u3 and so on and so forth. They can be equal also, right? There are the possibilities. Okay, and obviously the last term greater than equal to 0, right? Means all are positive. Okay, so what does it imply? It implies that or basically you basically mean that means all the terms are positive. That is the basic idea. Okay, so if this is the case, you just apply the limit as n tends towards infinity of un to the power 1 upon n. So this is the case. If this is coming to be suppose lambda, right? This is lambda. Okay. Okay. So it will converge. It will converge for lambda less than 1 and diverge for lambda greater than 1, right? Okay. I hope you understood. Okay. And for lambda is equal to 1, again there is no conclusion. Okay. I hope you understood it. There's something called Cauchy condensation test, but I don't think so it is in your course, but still I am telling you all, maybe if it comes, right? So that is why, but I don't think so it will come, right? Okay, so let's see. This is the fifth test, Cauchy condensation test. Condensation test, right? Okay, you all have understood what I have written, right? Okay. Okay, so let's see. The Cauchy condensation test means all the terms, the condition are of the means the condition of this only, that all the terms are positive right? So in this case, what is the case is that you evaluated this expression. This is convergent if this expression is convergent, right? To the power k, right? This expression is if and only if convergent, if this is convergent, right? Okay. There are many other ways to prove this, but we won't look into it. Okay. This is a basic idea, right? There's u1 plus that term, right? You will understand it. Okay. And here k goes from 0, and here I goes from 1 to infinity, right? Okay. So now let's sorry. Now come to some basic definition, and then we will see the problems, right? I hope it is a bit fast, which I'm telling, but it is basically for a revision like thing, right? And don't worry, it will be crystal clear when we solve the problems, right? Okay. So what is the alternating series? Alternating series, for example, if I say 1 minus 2 plus 3 minus 4 plus 5 minus 6, like this, when there is a change in the sign, in the polarity, means one time it is positive, one time it is negative, and so on, it is alternating like this. Okay, then we say that it is a alternating series. Okay, I hope you are understanding. Okay, so test 6 we are coming to. For alternative series we are coming to test 6, and that is the Leibniz rule. Let's see what is it. Okay, let's see the rule first of all, that how it goes. For example, if you have series like this only, u1 minus u2 plus dot dot dot, like this. Okay, so what you do in this is you will check numerically, means you will take the mod u1 mod u2 and so on and so forth, and you will check whether the numerical values are decreasing or not. For example, 1 negative 1 by 2 negative 1 by positive 1 by 4, and so on and so on, like that. It may follow some pattern, right? So in that case you will check the modular value of this quantities, right? Okay, and if they are decreasing, you will check limit as n tends towards infinity of u of n is equal to 0. If this and this condition are satisfied, means in this they are preceding or decreasing, right? And the limit as n tends towards infinity of un is equal to 0, then we say that the series is convergent, right? If it is not equal to 0, then we say that it's oscillatory, right? Okay, now we are coming to some more definition of conditionally convergent series. What are these? Well, let's see. For example, you are having u1 minus u2 plus dot dot, so on and so forth. So you compare it with this u1 plus mod u2 plus dot dot dot. With this, you are comparing with this expression, right? So what basically is happening is that in this case, if this is convergent, then this will imply that this is convergent, right? This is 2, this is first. So if the second series is convergent, then it will imply that the first series is also convergent, since obviously it has a greater magnitude than this. So if the greater magnitude has a finite value, then it implies that the lesser magnitude also will be finite, right? Obviously, right? Okay, so in this case, when this is convergent, then and this is also convergent, we say that so 2 is implying the first to be convergent, right? So it implies that, so this condition is known as conditional, sorry, absolute convergence, right? Absolute convergence, right? I'm not writing the complete spelling, but you should understand it. Okay, so it is known as absolutely convergent, right? This is absolutely convergent, right? This expression is the first one, right? And if this is divergent, if 2 is divergent, but the first one is convergent, then it is said to be as conditional convergent, the first series, right? Okay, I've understood the basic idea what I wanted to say, and now we will come to the questions, and it will help you all to understand the concept better, right? So let me raise this, and let's come to the questions. We will discuss many questions, right? Okay, so let's start with the first question. The question, it states that summation of un of where un is equal to n to the power 4 plus half upon 1 by 2 minus n to the power 4 minus 1 to the power 1 by 2, right? This is the question, right? So in this we will use the ratio test, right? Because you will face bit difficulty in integrating this stuff, right? So we will use ratio test, the maybe we can use comparison test maybe, right? In that case, so I told that you take the ratio and take the limit as n tends towards infinity of un upon vn, and you solve for the expression. But how you take the limit, that is a big question, right? So first of all, we can take this expression in the denominator, which will make the things simpler. How? Let's see. Observe, you can write this expression n to the power 4 plus 1 raised to the power 1 by 2 minus n to the power 4 minus 1 raised to the power 1 by 2. You can write it like this: 2 upon n to the power 4 plus 1 raised to the power half plus n to the power 4 minus 1 raised to the power half, right? You can write it like this. You all can check it by rationalizing it. I won't discuss it. You all can check, okay? Just multiply by its conjugate, you will get this thing, right? Okay. So this is your un, okay? So you got un. How you get vn? Well, let's see. The vn you can assume as the power of n, the final power of n. For example, n upon n cube plus 1. In this you will assume vn is equal to n by n cube, which is equal to 1 upon n square, right? This power upon this power, you get this, okay? So over here you get 1 upon n to the power 4 of half is equal to 1 upon n square is equal to vn, right? You got this thing, okay? So you get limit as n tends towards infinity of un by vn, you get this thing. What do you get? 2 upon n to the power 4 plus 1 raised to the power half plus n to the power 4 minus 1 raised to the power half upon 1 upon vn, and it will go upwards, it will become into n square, right? Since vn is 1 upon n square, so 1 upon n square, 1 upon n square, it will n square will go upwards, right? Okay, I have you understood it. So you get limit as n tends towards infinity of 2n square by n to the power 4 plus 1 raised to the power half minus plus n to the power 4 minus 1 raised to the power half, right? You get somewhat like this, and it is a limit which you can solve, and on solving you will get 1, and 1 is a finite value, right? So 1 is a finite value, okay, which means un and vn will be convergent and divergent together, right? So let's see what is vn. Vn is equal to 1 upon n square, right? 1 upon, let me change the chalk, right? Okay, so 1 upon n square, right? And you all know that 1 upon n to the power p is convergent if p is greater than 2, right? So if p is greater than 1, so you get vn is convergent, which implies that this expression is also convergent, right? Okay, from the comparison test, right? You can go back to that section and you can study again, right? So let's move to the further questions, right? We will discuss some important questions which can build your concept, right? Okay, we have very less time, so that is why I have to be in a bit hurry, right? Okay, so let's see some nice question. If let's do one more question. 1 upon 1 into 3 plus 2 upon 3 into 5 plus 3 upon 5 into 7. So let's make a general term in this, the un, right? How you will write un? Well, let's see. The upper terms are just a consecutive natural numbers, so you will get n. The denominator is the consecutive odd numbers product. You get 2n minus 1 into 2n plus 1, right? You got this, okay? So in this case, what you get n upon 4n square minus 1. You get this stuff, right? Okay. So in this case, what if you apply the comparison test? In this case, you will get Vn as n upon n square. You get 1 upon n, right? Okay, you get this. So you get un by Vn as n tends towards infinity. You get n upon 4n square minus 1 into the 1 upon n will go upwards. It will become n, and it is equal to n square by 4n square minus 1 as n tends towards infinity. And you can solve it by several methods, and you will get the result as 1 by 4, I guess, right? This is finite, which means they both will be convergent or divergent together, right? Okay, but 1 upon n, the summation as 1 upon n is a divergent series, right? 1 upon 1 plus 1 upon 2 till the infinity is equal to infinity, means it tends towards infinity. Saying it equal to infinity is wrong, means it tends towards infinity, means it is not a convergent series, which means the expression is divergent, right? Okay, I hope you understood. Okay, now let's move to the second question. Let's see. Try to grasp the things in a more logical way rather than rote learning. It will help you all more, right? Okay, so let's see the question number 2, means whatever number. 2 raised to the power 2 upon 1 to the power p plus 3 upon 2 to the power p, and so on and so forth. What do you get? Well, n plus 1 upon n to the power p is equal to un. What is vn? Vn is equal to n upon n to the power p, which is equal to 1 upon, right? Okay, right? Okay, so limit as n tends towards infinity of un by vn, you solve it, you get n plus 1 by n to the power p into n to the power p minus 1. You get n plus 1 by n, as n tends towards infinity, it will be equal to 1, right? This is finite again, so it will depend upon vn, and vn, since we know that 1 upon n to the power x is convergent if x is greater than 1. Here x is p minus 1, so p minus 1 is greater than 1, so p is greater than 2. So this expression is convergent if and only if p is greater than 2, right? Everybody understood? Okay, that is the basic idea. Okay, now move to the next question. Let's see. The next question states summation as n goes from 1 to infinity of n square by 3 to the power n, means you are given un n square by 3 to the power un, right? In this you can't apply the comparison test, right? I hope you are understanding it, right? So in this you can say it is 3 raised to the power n, which means you remember Cauchy root theorem, Cauchy root rule. In that, what you are doing un raised to the power 1 by n. So in this, if you do raised to the power 1 by n, this 3 raised to the power n will vanish. So it will make the calculation very easy. So let's do it. You raise both sides, you apply Cauchy root theorem, right? In this case, okay. So in this case, you will get n to the power 2 upon n upon 3, and you get limit as n tends towards infinity of n to the power 2 upon n by 3. And I guess if I am not wrong, this is equal to 1 upon 3, right? If I am not wrong, the limit as n tends towards let's solve this limit. I hope you all know how to solve, but still let's solve. N to the power 2 by n, let's say it equal to L. You take ln L, you get ln n square, or 2 you bring it out and you get by n, as n tends towards infinity. I'm not writing this due to the shortness of time, but you all know that it is going towards infinity, right? Okay, let me write it only like this. So ln L, and you apply the L'Hopital rule, you get 2 upon n, and as n tends towards infinity, you get L is equal to 1. Okay, so this is equal to 1 by 3. Okay, so it is less than 1. So Cauchy root theorem states that if this expression, the limit is less than 1, then the limit is convergent. So series is convergent, so this is convergent, right? Okay, simple idea, simple thing, right? Okay, okay. Sorry. Okay, so now let's start another question. X plus x square by 2 plus x cube by 3, so on and so forth till infinity. So you are getting x to the power n upon n, right? This is the un. Very simple, right? So again you say see a power of n. So what? When you see the power of n, you again apply the Cauchy root theorem, and in this case you will get x to the power n by n raised to the power 1 by n, right? You will get this. Okay, so when you get this, you just solve x upon n to the power 1 upon n, as n is tending towards infinity, right? Obviously you should write the complete statement that what you are doing. I am just here to guide you also, that is why I am just writing like this. Okay, so basically you get the limit as x. So it means this is convergent when x is less than 1 and greater than 0, right? Okay, so that is the thing. Okay, basically you can say this thing only, and it is divergent for x is greater than 1, right? Okay, okay. So now let's see the next question. Okay, the next question states that the sum as n goes from 1 to infinity of n upon n plus 1 raised to the power n square, right? Again you see that un is equal to n upon n plus 1 raised to the power 1 raised to the power n square. You can see a n power, right? So in this, what you will do, you will again apply the Cauchy root theorem, and what you will get is that n upon n plus 1 raised to the power n square, and as un is equal to this quantity, so what we will get, so now we will apply the Cauchy root theorem, and in this we will get un raised to the power 1 by n. You get limit as n tends towards infinity of n upon n plus 1 of n square by n. You get limit as n tends towards infinity of n by 1 plus n raised to the power n, right? You get this, and notice that if you do it like this, limit as n tends towards infinity of 1 plus 1 upon n, just notice I have reversed the things, negative n, you get e raised to the power minus 1. This is a tricky part, you should understand what I have done. You know that limit as n tends towards infinity of 1 plus 1 upon n raised to the power n is equal to e, right? You know this. Okay, so just we are doing that thing, and in this I just reciprocated this, right? Okay, so let's move on to the next question. Since it is less than 1, it is 1 upon e, which is less than 1, which implies this series is convergent. Okay, so now let's move to the next question, right? Okay, so let's see, the next question is this one you will do on your own. The summation 1 plus 1 upon root n raised to the power minus n raised to the power 3 by 2, you will apply again the same thing, and you will end up getting this thing, right? Limit, you will end up getting limit as n tends towards infinity of 1 upon root n raised to the power negative root n, right? You'll get this, and you will again get this quantity, right? You all can solve it and check, right? Just apply Cauchy root theorem again. So whenever you see a power of n, you apply Cauchy root theorem, right? Okay, now let's see another expression for let's see for alternating series also. Okay, so let's see for the alternating series, you get 1 upon a minus 1 upon a plus b plus 1 upon a plus 2b, so on and so forth, for a comma b greater than 0, right? Okay. So let's write the general term. What we get? We get negative 1 raised to the power n minus 1, as n goes from 1 to infinity, right? Of 1 upon a plus n minus 1 into b, right? Okay. So either you can apply the DLM bars over here also. You can apply that. Let's see. But no, you don't need to actually. This is the alternative series, so there is only one rule in this, the Leibniz test. What you will do is, you will check the mod first of all. So 1 upon a plus b, 1 upon a, 1 upon a plus 2b, since all are positive terms, so it is gradually decreasing. That means the first condition is tested, right? Now check the second condition, the limit as n is tending towards infinity of 1 upon of un, sorry, of un, and it is equal to limit as n tends towards infinity of 1 upon a plus n minus 1 into b, and this is equal to 0 in fact, which means this series converges. So it is satisfying the Leibniz test, right? Okay. So now let's see another question. I have to be in a hurry because uh, we don't have much time. That's why. So now let's see the next question, and it states, show that the series cos of pi n by n square, n goes from 1 to infinity, is convergent. So at first when you see this term, you get panic that how we will solve the trig function over here. So basic idea is that when you substitute 1, you get cos of pi, and when you substitute uh, you substitute 2, you get cos of 2 pi, means it is the auxiliary function, it is going from plus 1 and negative 1 only, right? So basically it is written as negative 1 upon n square plus 1 upon, means 1 plus 1 upon 2 square, and so on and so forth, right? Which is basically when you so now in this you will check for the convergence using absolute and conditional convergence, right? So in this, how you will check? You will use 1 upon n square term, right? In this is somewhat like this, negative 1 raised to the power n by n square, right? In this case, so you have just applied the mod, and you got this. So this, as p is greater than 1, so it is convergent, which implies that this expression is absolutely convergent, right? So which means this is also convergent, right? You all know, remember that theorem, na? That in mod we were writing like this, u1 minus u2 and so on and so forth, and I was saying take the mod and just add them, right? This thing. So if this expression will be convergent, then this will imply that this expression is convergent, and that is known as absolutely convergent expression, this one, right? And if this one is diverging and still this one is converging, then it will say that it is conditionally convergent, right? Okay. So now let's come to the next question, right? If you have any doubt, you can comment me or message me, right? So let's see one more question. The question states, show that the summation as n goes from 1 to infinity of 1 upon n factorial is convergent. We have to prove this. So it is a very simple expression, right? So in this you will apply D'Alembert's test. How? Let's see. Let's see if we apply the D'Alembert test, what we get. Okay. You will get limit as n tends towards infinity of u of n plus 1 by un, right? You got this. Okay. You will get 1 upon n plus 1 factorial into n factorial, as n is going towards infinity. You will write like that, limit as n goes to infinity, right? Okay. So I hope you are understanding it, right? Okay. So you get n factorial upon, you can apply the property of factorial, that n factorial is equal to n into n minus 1 factorial. You apply the same thing over here, n plus 1 into n factorial, you get cancelled, right? N factorial gets cancelled, and this is equal to 0. And in the D'Alembert's test, if the lambda comes out to be less than 1, then we say that the series is convergent. So this means this series is convergent, right? Okay, you have to just remember that how the things are going, and then you can calculate it. Okay, so now let's start with okay, so we will see one more question in this, and in this we are given that x upon 1 plus x minus x square by 1 plus x square plus x cube by 1 plus x cube, so on and so forth. So, and here we are given that x is lying between 1 and 0, right? So this is again an alternating series. So in this we will apply just that thing, x upon 1 plus x, and what is the next term? It is x square by 1 plus x square, and notice that it is again a decreasing series, right? How? X upon 1 plus x, imagine if it is you can write this as 1 upon 1 plus 1 upon x, right? So you get 1 upon 1 plus 1 upon x. Just imagine if this is less than this expression, means the next expression, means you are assuming this, right? You are assuming this, okay? 1 upon x square, you just solve this, you will get 1 upon x square, 1 plus 1 upon x square less than 1 upon 1 plus x, right? You get this, and you get, on solving this and this will get cancelled, and when you will reverse you will get x square is greater than x. But this is wrong in this domain, right? Which implies that this inequality is wrong, and you will get this inequality, means it is a decreasing expression. So we will get, so we can directly write that limit. So the first test is verified, means the first condition of the Leibniz test. So we will apply the second condition as n tends towards infinity of x to the power n upon 1 plus x to the power n, right? You will get this, and when you solve limit as n tends towards infinity 1 upon 1 plus x to the power negative 1 negative n, right? And notice that since it is between 0 and 1, means for example 0.5 raised to negative infinity, what you will get? Imagine you'll get 1 upon 1 plus 1 upon this quantity, and you will get over here 1 upon 0, right? You will get this, means you will get 1 upon means 1 upon 2 raised by infinity, just imagine. So this is equal to, in fact, 0, right? So this is the condition, okay? So this will be equal to, just a minute, yeah. So notice that x is between this quantity. So if you get if you check in this domain, for example x is equal to 0.5, just to verify you can imagine 0.5 raised to the power negative infinity, you got this. So you get 1 by 2 raised to power negative infinity, which is equal to 2 raised to power infinity, right? Which is equal to, which is tending towards infinity. Obviously you can't write exactly infinity, but just to explain I'm writing. So as n tends towards infinity of 1 upon x to the power negative infinity, this is equal to 1 upon 1 upon infinity, which is equal to 0. Since this limit is satisfying and we are getting this, so we will get, so we conclude that this is convergent, right? So that's it. I hope you all understood the lecture, and if you like this, then please do like, share, subscribe my channel, and thanks a lot for watching. Bye bye, take care.